What's up, everybody? So let's do a little bit of stream work in the lab. Pretty surface level stuff. I didn't get too deep on this. Hopefully this one's fairly easy for everybody. And more work's been coming in, which is great. I appreciate it. Keep it going. So let's look at the general pattern of how streams tend to work. Up higher in the basin, they'll tend to be steeper until they get down towards their mouth, where what they flow into. They'll tend to be more gradual. That elevation that we're talking about right there is the base level. That's the elevation of the body of water that river in question would flow into. Take the Oswego River, for example, right in town. Its base level would be the elevation of the top of Lake Ontario. Higher up in the basin, go way to where that basin begins, which the Oswego River drainage basin is huge, and go all the way down to Lake Ithaca, water from Ithaca, up on the hill. What do they call that? Buttermilk Falls. That all flows down into the Finger Lakes, flows up north, over towards Syracuse, and then up to the Oswego River. Higher in it, this is the case. It's steeper. And then as you get up north of Syracuse, it tends to get a lot flatter, right? What do we mean by drainage basin? I'm just popping this up as an example because this is a project that just got started in my neck of the woods. Sterling Creek. The definition of a drainage basin would be the area of land drained by one stream system. So all of the land within this orange blob right here, which includes where I live, all flows out through Sterling Creek. In fact, the corner of my property has one of the tributaries of that in it. Go over this line, even if it's subtle, in the rolling hills of southwest Oswego, go over this line, and that water is going to flow into a different stream system. Go over the line this way, again, it will flow into a different stream system. So that area of land is what we consider a watershed or drainage basin. And these projects and many others like them are meant to restore. And that begins with just raising awareness of what they are and how the human activities on the surface may impact that. Without getting too distracted, though, in a broad sense, higher in that drainage basin will tend to be steeper, lower in that drainage basin will tend to be flatter. And along with the steepness, you'll also get the shapes of the rivers doing some kind of funky things. And we're going to calculate those shapes with something called sinuosity, which is fairly easy. All you do is you take the length of the stream channel, everything, by going right along it and running those numbers. How long is the stream? And then dividing that by the straight line distance between the 2 points. So let's ignore B for a minute and just use A and C as endpoints. For A, if you measured from here to here along the stream, and then measured from here to here, like as the crow flies, those numbers are going to be pretty similar. So it's going to be a similar number on top and on bottom. And when you divide similar numbers, you end up pretty close to 1. Whereas in this case, if you measured this distance and measured and measured and measured and measured and measured, you're going to get a much higher number divided by that distance between them. So what's going to happen to your sinuosity? That's what we're going to figure out in your first couple of questions. The 2 examples you're going to use are going to be from A to B on this map, you'll do a sinuosity, and from C to D on this map, you'll do a sinuosity. But first, we'll do it in Google Earth together. And if you look at your answer sheet, which would probably be a good idea if I pop that up, yeah? All right, there we go. Popped up. Chittenango Creek, south end, Chittenango Creek, north end, and then the Bighorn River and unnamed tributary. Those will be the ones in the book. So I'll help you with these first 2. Hopefully that kickstarts where we're at. So I already did the work in Google Earth to say, here's a section in North Chittenango Creek, that white line, where that's how the river flows, and then we'll measure a distance. And then south over here. Now, if you're not familiar with the area, first off, it's a beautiful drive if you ever go between Chittenango, which is right up here, and Casanova, which is right up here. This is the high side. This is uphill up here. In fact, we can look at it in Google Earth here. Oh, I got to turn on that feature, though. Turn on this. So let's say at the top of my line, I'm up around 1,023 feet, and at the bottom, 541. So it's a pretty good drop. And it's, like I said, it's a beautiful drive. Chittenango Falls State Park is in there. Check it out. Whereas if I do over here, we're going to see it's a lot flatter. I'm at 410 down to 370. So that only goes down by, 40 feet that whole time versus the hundreds over here. So much steeper hill coming down off this broadly in New York State south of this line right here, where the main train route and the thruway and the Erie Canal all went through. Surprise, surprise. That's the kind of the line where south of there is very hilly, which would have been impractical for trains and canals, and north of there is very flat. So while we're in this very hilly section, with the source of the water being Cazenovia Lake here, I chose that section to measure. So let's do the work. What do we got? Chittenango Creek, the south end, the channel length is already, Google Earth does the work for us. There, it turned red, and it's 4.19 miles. So tracing the creek there, where it's, I'm not saying it's perfectly straight, but it's a little curvy, is 4.19 miles. All right. Pause if you have to. That's where you're going to chuck, and that number right there. Straight line length is going to be, we'll cancel that, and we'll do a straight line in miles. So it's really kind of a ratio problem. If I do a straight line from where I started, right about there, let's do the map length of they're both the same, 3.55 miles. So there's your two numbers that you'll chuck in there. Rewind if you must. Your straight line length would be 3.55 miles. So calculating sinuosity, that's just dividing, should be pretty straightforward. With the lesson being that there's the division problem again if you lost it. The closer you are to 1, the straighter the stream is. And then the thing we got to link is that generally the steeper the hill is, the closer to 1 that'll be. The lower the sinuosity value will be, indicate a more straight stream. Because water doesn't mess around. It just goes down those hills, right? If it's a steep hill, it's going down them. This is more of what we'll see in a flat area, like Chittenango Creek North. So your next section on your answer sheets, Chittenango Creek North, we'll do the same exact thing and see how it changes for a flatter area. Clear that out of there. And you can see, look at the white line. In fact, if I do this, it turns red. You can see how much more wavy it is, being that it's a much flatter area. In its measurements, we went 12.2 miles there as the channel length. And then distance, if we do like a straight line distance to its base level, which is Oneida Lake, 5.61 miles. All right, so compare those values with what the stream looks like with all of those meanders, with the idea that it's reasonably flat here and quite hilly here. That's the goal of the first part. Then you'll do it again on your own for these two, the Bighorn River between A and B, and the unnamed tributary from C to D on your map right here. All right, and look, you guys, if you don't know topo maps, some of the parts of this lab might be tricky. But if you know them by now, where all these lines are all close together, that's our indication of a very steep hill, and we got a pretty straight stream there. I know this is going to be a little tricky on the computer screen. Don't panic. Get as close as you can to how long that river is, and how long that river is. And those are using this scale right here. All right, that'll be that. And then here I'll have you. Oh, never mind. Yeah, and then relate the gradients and steepness with sinuosity. All right, let me pause quick. Sorry, I'm a little sick today. All right, the next section. Do this bit of reading here where you're going to think about the steepness of the sides of the valleys and kind of loosely the age of the river, how long it's been doing its thing, right? If it's very steep on the sides, that's a young river cutting into the ground, usually accompanied by some uplift to the crest. But as it matures and meanders, that'll be where it can widen out a little bit. So it's a pretty distinct difference between this and this. That's really all the next section gets at. So if you look at it topographically at the Genesee River, which is in the lab, sorry, lots of monkeying around here. Going back up to there, can you describe, don't worry about trying to run numbers on this thing, the difference between those, like that creek right there, and then the Genesee River. This would be south of Rochester. If you've ever been to like Letchworth State Park. Um, that's kind of the area we're looking at here. All right, so that should do it for 2. This one you'll have to think about a little bit about, guess, but you can try to deduce it, see what you can come up with. All right, 3 will be based on the next section we're reading, with the different features that can evolve within a meandering stream, like the floodplain and all of that. And one thing I didn't love is that they don't necessarily have the name of the other side, and it's a question I asked. I wrote the question, then I came back and it didn't say it. So point bars will be like the insides of the streams, where you can see that gravel sediment is accumulating. The other one that it doesn't say, cut bank. That's going to be the outside, cut bank. On the outside, with the water going faster, it erodes into the land, cutting into it. The inside, it goes slower, which allows it to deposit material. So I did some areas just down here on the lower Mississippi, and you can go anywhere and see these features. I just randomly picked a couple when I made the lab. There's somewhere you can really see the sand come out pretty well. All right, let's go in here. This is going to give away the answers, but it's all good. Thanks for watching the video. On the inside, you can see that there's sand. That's going to be your point bar, where it builds up and builds up and builds up because the water's going slower. On the outside would be where it cuts into the land, cut bank. And you can even, and I think this hint, this will be one of the midterm questions. There's one I've got somewhere about how trees fall in on this side. If trees are falling in, why would trees fall in? Because the sediment erodes, exposing the roots, and they fall in. That's less likely to happen on the inside where sediment lands because the water is going more slowly. Chat a little bit about that, and you'll be in good shape over there. Read there. Think about floodplains, and you'll be good. Then the last one I got, like I said, this one's hopefully pretty easy. Read a little bit about the drainage patterns. Water goes downhill. There's your golden rule. You're going to meet people in your life that will say, "Oh, water's got to flow south," and that's like this misconception that happens. And I've got it down to 2 things. One, maybe it's the Mississippi River flows south, and that's a big one in this country, right? Another, and as silly as it sounds, I think people are used to holding maps like this, and they think that down has something to do with it. But south on a map isn't down on Earth. Like, the map is like this. Things flow downhill. Like if you flip a map over, all the rivers on Earth suddenly change course. I don't know. One of those 2. Either way, get rid of the rivers flow south thing in your head. It's not a thing. Oswego River flows north. Chittenango Creek flows north. So what downhill is where the water is going to flow, and then what's going on the land, like what is the shape of the land, what is the shape of the bedrock, is going to determine the pattern for where the water flows. Whether it be dendritic, like tree roots. Trellis is in a valley and ridge where it's got to flow down the steep sides, then out the valley floors. Some radial ones, and those are the annulars of the rarities in there. So I just gave you a couple photos and said, what's it look like? Things I shot in Google Earth. What's that one look like? What's that one look like? What's that one look like? Explain it in touch, and that's it. You're good to go. Hopefully a fairly easy one. Thanks for tuning in, everybody, and good luck. Shoot me an email if you have any questions.